Hello everyone, I hope you are doing well. So in today's video, we are going to basically be continuing off the VCE chemistry exam part 2 of the short answer questions. And so like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 6. Scientists are currently researching an experimental secondary cell. The following reaction takes place in the experimental cell during discharge. Alright. A diagram of the experimental cell is shown. Okay, we have carbon electrodes, and we have H plus ions, meaning that it's acidic. And yes, we have those. Alright. State the energy transformation that occurs in the experimental cell during discharge. Beautiful and easy question. Remember, discharge is basically taking chemical energy from those reactants, taking those chemical energy and transforming it into electrical energy. So, chemical into electrical. That's what discharge is. It's that transformation. So chemical energy into electrical energy. Which reactant is the oxidizing agent in the experimental cell during discharge? Use oxidation numbers to justify your answer. So we want the oxidizing agent. And remember, the oxidizing agent is the one that's being reduced. So reduced. So let's have a look at those reactants. Which one is the oxidizing agent? So we have two reactants, as we can see. The way you would actually, remember that the oxidizing agent, which is the one that's being reduced, reduction is where electrons are always on the left-hand side of the equation. So what I'm going to do here is the most easiest, like in terms of using oxidation numbers, the most easiest element is the iron element. Because there's only one iron element here, and there's only one iron element on the right-hand side of the equation. Now, what's the charge of this ion? I straight away know it's a +3. And you're probably like, how? How did you straight away know? Easy, because of this hint here. Now, let me explain why. If you have a Fe3+, like for example, this is a Fe3+ ion, and SO4, which is always a 2- charge. When they combine, these here switch. So you see that charge 2 is going to be here, and that SO4 is going to be on the third, so 3 here. And that's why it looks like this. So this has to be a +3. The ion initially was a +3. So let's have a look at it in this here. This ion here. This I already know is a +2. Same thing. If we have an ion, which is a +2, and an SO4, which is also a 2-, when you add them, those charges cancel out. Hence, you get FeSO4. So it has to be a 2+ initially. So now, let's see what's happened here. So we basically had on the reactant side, Fe3+, and it basically went to Fe2+, all right? Now, we want to make sure that charges are equal, so we have to actually add an electron on the left-hand side to make those charges equal, and hence, remember, electrons are on the left-hand side. This is the one that's being reduced. So if this here is being reduced, this whole molecule is being reduced, this tells me that it is our oxidizing agent. Beautiful. So, Fe2SO4, let's write that down. So oxidizing agent is basically Fe2SO4 3 aqueous. Beautiful. And we use oxidation numbers, so that's oxidation numbers went basically from, for Fe, went from, we started off +3 and we went to +2. These are our oxidation numbers. Beautiful. That should give you those 2 marks. Nice. Next one is C. Write a half equation for the reaction that occurs in this half cell during recharge. So for these here, when it's recharging. Easy. So the way that I would do this is basically look at the discharge equation. Here it is. So this is the discharge equation for that. And I'm going to look at those components. This component here, these two. That's what they were telling us. So let's write the equation. So we start with C14, H10, O8, S2 aqueous. And basically went to C14, H8, O8, S2 aqueous. Now we can see that everything's the same except the hydrogen. There's 8 hydrogens on the left and there's 10 hydrogens on the left and there's 8 hydrogens on the right. We need to plus a 2 H plus to compensate. So now they actually have the same equal hydrogens. Now, because we have a 0 charge here overall on the left-hand side, but we have a +2 charge because of this here, we need to add 2 electrons on the left to cancel that charge out. So basically here, this here is what's going to happen. This is the half equation that's going to be occurring for the discharge for these components. This is your discharge. So discharge. Now for the recharge is very easy because all you have to do is basically flip it. Flip this. So make this as your reactant and make this as the product. So like this. So I'm just going to basically copy this. This is going to be my reactant. And this basically goes to this over here. This here is my product, and hence this is my discharge. This is my recharge equation, and that's what we needed for that question. So let's go bring it down here. Let's write it in a nice different color. Let me leave it here and let's write it down. So write the half equation for the reaction that occurs for this cell during recharge. So remember, it just flips. So let's write that down. So it's a C14 H8 O8 S2 aqueous plus 2H plus aqueous plus 2 electrons, and that all goes to C14 H10 O8 S2 aqueous. Beautiful. State the polarity of this half cell electrode during recharge. Easy. Now, if this is on recharge, can you see how on the recharge, this is our recharge equation for that basically half cell. We can see it's going through reduction, which basically occurs at the cathode. And remember, in electrolytic cell, remember it's recharging, so it's acting as an electrolytic cell. Remember, if it was a galvanic cell, what do we know about the cathode? The cathode is basically positive for a galvanic cell. Because it's acting as an electrolytic cell, remember what is the polarity when it's acting as an electrolytic cell in the cathode? It is a negative. So make sure you put negative. So negative. Beautiful. Explain how the polarity of the electrodes is established during recharge to allow the recharge to occur. Easy. So, I remember, I think a lot of students still get confused in terms of what is recharging? What happens when you recharge? Let's start off the basics. Let's make up a scenario. That's what best way that I would try to explain this question. Say we're creating a galvanic cell right now. This is a galvanic cell. I'm going to write basically a galvanic cell. You have a galvanic cell. And say we were reacting. Let me just basically look at my, let's say we react to stuff that's spontaneous. Let's say we react, for example, chlorine gas and sodium chloride. So yeah, sodium. Say we were reacting these two here. So basically what will happen is at the cathode, remember, CO2 gas plus 2 electrons will give us 2Cl minus aqueous. On the anode, where oxidation occurs, it's basically going to be Na solid goes to Na plus aqueous plus electrons. Let me explain why I'm writing this. Let's have a look at what happens. So basically, this is a spontaneous reaction. If we have like a nice cell here, nice galvanic cell. Of course, I haven't kind of separated. I haven't used a salt bridge and stuff, but who cares about that now? Just have a look at the understanding what's happening. Of course, it won't work because we don't have a salt bridge, of course, and and you don't want these basically, imagine you have like a little separator. Basically, they don't touch, that NaCl and that chlorine gas, because if they basically touch, they basically form NaCl, and hence we don't want that to happen because they'll spontaneously react. So we have two electrodes. We have two electrodes here. Two electrodes. And let me copy that and duplicate this over here. Let me duplicate the whole thing. me duplicate the whole thing here. There it is. So let's say this side here is your anode. Actually, let's call it cathode. Let's start with the cathode here. Say this is your cathode, and this is your anode. And normally for a cell, for a galvanic cell, the cathode is basically positive, and the anode is normally negative. That's what it is for a galvanic cell. And basically, we know electron flow flows from negative to positive. So anode to cathode, so negative to positive. That's where electron flows. And so because, of course, our imagine this is chlorine gas, of course, here. Imagine that part here is chlorine gas. Of course, it's not going to react. There's no chlorine gas electrode. You would normally use an inert electrode with like a glass tube that fills in chlorine gas. But we'll leave it in this case like this. And this here is our NaCl, our sodium chloride. It's like our sodium. And basically, yes, this is how your cell is going to look. Beautiful. That's how a galvanic cell looks. But what happens when it is a electrolytic cell? Be careful. The polarities don't change. It's not the polarities that swap. It's the oxidation and reduction equations. This is why. If you look at your cathode and anode, yeah? Say, for example, you have this chlorine gas and this sodium, and basically they react. They react spontaneously, and hence we form all these two chlorines and Na plus ions. And then, okay, we form those, but then we run out of, chlorine gas and Na ions, and the reaction has stopped. If we want to recharge it, it has to act as an electrolytic cell. How do we recharge it? We have to swap these flip these equations. Because think about it, if we flip it, we make these as reactants. Remember how we have all these right now? All those two chlorine minus? We have them all right now because, and we can use them, if we flip the equation, they become the reactant and we then form more of that chlorine gas. Hence, we basically re-establish our reactants, like re-get them. So, for example, if I flip this equation here, so let me write it here. If I flip this equation, let me do it here. So that, kind of duplicate here, that. If I flip this, there it is, and take this, and bring it here, duplicate this, flip it. Now you can see that, how we use basically for, galvanic cell, we use that Cl2 and we form all these 2Cl minus and all that stuff. Now, when we run out of that Cl2, we want to, remember, recharging is basically bringing these back. And so to recharge it, if we flip the equation, look at that. Now we have Cl2 as our product. And because how we have all these. So we basically flip those equations. Now this, remember what we said, electrons, if they are on the right side, it's going to be our oxidation reaction, which occurs is the anode. Now this here is going to become our reduction, which is our cathode. So overall, what happened? It's just they flipped. So for example, it's actually your cathode and your anode that flipped. So these two here, so if I take this, not the actual polarity. So this here flipped, these here flipped. This is now your cathode and this is your anode. So it's not the polarities that change. Be careful with that. Not the polarities. Okay, so we got those. And so remember, your anode is where electrons are supposed to... So let me take these electrons out now. Remember, your anode is where basically, of course, oxidation occurs. And basically, it's the loss of electrons. So electrons are going to try to get out on that side. And remember, cathode is where reduction occurs. And it's the gain of electrons. So you want electrons to come to that... to come to this electrode. So we want the electron flow to be this way, coming out of the anode, going to the cathode. But how do we attain that? We need a battery. We need an external power source to basically force those electrons to the cathode. That's what we need. We need to basically, like an external power source, like a battery, that will force them to this negative electrode and hence create it as basically like a cathode. And again, yeah, that's what it is. And so basically, because we use the external power source to basically reverse the flow of electrons, this is a non-spontaneous reaction. And hence, we basically get our original reactants back. And yeah, we have recharged the cell. And that's it. I hope that makes sense. How we basically, so not the polarities that change, it's the oxidation reduction reactions that swap. So be careful with that. So let's now write a nice equation for this. All right, so let me take this back here. And let's write a nice response. I'm going to just put it at the bottom here. Hope that makes sense. All right. Okay, so let's write. So for 2 marks, I'm going to kind of be in detail. So we're going to say during recharge. So during recharge, an external power source, is applied to the cell. That's the main thing. The power source, we know the power source. So the power source basically forces electrons into the negative electrode. Yes, yep, into the negative electrode. Hence occurs at the cathode. The other electrode where oxidation occurs. So oxidation occurs, basically the loss of electrons, remember loss of electrons, becomes the anode, which is basically the positive terminal. And so overall, the external power source reverses the flow of electrons, to drive non-spontaneous reaction, to drive a non-spontaneous redox reaction. To restore reactants. To restore original reactant, we want to say. Sounds good. Explain how the polarity of the electrodes is established during determine how the polarity of electrodes is established during recharge. Yeah, so during recharge, an external power source is applied to the cell. The power source forces electrons into the negative electrode, occurs at the cathode. Yep, the other electrode where the oxidation occurs, loss of electron becomes the anode. And so the external power source reverses the flow of electrons to drive a non-spontaneous redox reaction to restore the original reactants. Yes. Beautiful. Sorry, I don't write here, but you put a battery here, basically. You need a battery. You put the positive. This is your positive and negative. And so you remember, electrons flow this way. So that's what we want. So we want to put a battery. That's it. Do we need to say like you put a battery on the positive side of the anode and the negative side of the battery we put it on the cathode? Do we need to put that? Explain how the protocol is stored during recharge. No, I don't think so, yeah. But yeah, that hopefully makes sense how it is able to recharge. So you need an external power source, yep. Next question, 7. Molecule V contains only carbon atoms, hydrogen atoms, and 1 oxygen atom. The max spectrum of the molecule V is shown below. All right, so this is molecule V. What do we see? So, okay. State the molecular formula of the molecule V. Justify your answer by using the information in the mass spectrum. Easy. So what we're going to look at that is the molecular ion peak, which is this one over here. Remember, this one here that has 100 intensity, this is your base peak. We want the molecular ion peak, and what's the number? 1, 2, 3, 4, 5, 6. It's 86, basically. So 86. Now, so basically the molar mass of the molecule is 86. Now we know it has already 1 oxygen atom. So imagine you minus, so 86 minus 16, because you remember, if you take 1 basically oxygen atom, we should have a mix of carbons and hydrogens that should add up to a total of 70 molar mass overall. How do we know what that is? Now, basically what I'm going to use is, I want to say it's like there's no double bonds. That's the first thing that I believe. Let's say there's no double bonds. So the rule for no double bonds is like Cn, H, 2n plus 2, meaning that let's say it's C equals 4. It means H has to be 4 times 2, so 4 times 2, which is 8, and plus 2, which is 10. So does that basically equal 70? Or is that close to 70? So 4 times 12 plus 10. No, 58. It's still small. What about if I put a 5? Let's say if I change this to a 5 here. So 5 times 2, which is 10, plus 12. So let's try that. So 5 times 12 plus 12. That gives me 72, which is actually close. So yeah, it's probably a C5. So it has to be like a C5. And then this has to be like a 10. Because if we have 72, basically, if we got this produced 72, which is close to this, it means just basically two hydrogens are out, which is 10. So it could have had like a double bond, or yeah, somewhere it has to have a double bond. So this is our actual molecular formula. So let's write that down. So C5H10, let's write that nicely. So C5H10, and there has to be an oxygen. So let's just double check if that does equal to 86. 5 times 12 plus 10 plus 16. Sorry, what am I doing? Hey, 5 times 12 plus 10 plus 16. That equals 86. Beautiful. So this is the molecular formula for, and justify your answer using the information. Quite easy. You just have to say like the molecular ion peak is 86 joules per mole, which means this is our molar mass, which means the molar mass of V is 86 grams per mole. That is it. So yep. So the molecular ion peak is that, which means the molar mass is that. Beautiful. Stay while there is a small peak at, mass to the ratio of 87. So, you have like this little extra part here. Now, this is easy. Now, remember, we consider all carbons to be like a molar mass of 12, but there sometimes are isotopes of carbon. Remember the carbon-13 isotope, which means that there's just an extra one molar mass. So that extra one could have been from a carbon-13, or could be like, let's say one hydrogen had it was a isotope, so a 2H, like a 2 hydrogen isotope. So, but the most kind of usual one is carbon-13 isotope, so put carbon-13. I wouldn't say the H+, but H2+. Just use the carbon-13 isotope. So, yep. So the peak probably represents carbon. So let's write this. So the peak probably represents carbon-13. Carbon-13 isotope. So there has to be like a carbon-13 isotope. Beautiful. The HNMR spectrum of molecule V is shown below. All right, so we have 1, 2, 3. We have therefore 3 proton. So what am I? 3 hydrogen environments. Hydrogen environments. All right. Beautiful. Okay. So start with information. The doublet at 1.1 parts per minute provides about the structure of molecule. Easy. So normally when you're doing like the proton NMR, you have to use the n+1 rule. It's like the best thing. It's like the easiest thing to use to learn about the structure. So because we know it's a doublet, we know if we use the n+1 rule, so n+1 equals what? It was a doublet, so it has to be 2. Hence, n equals 1. What does this tell us? It tells us basically like the adjacent side of the carbon. So the adjacent side of the carbon has to have 1 hydrogen. Let's think of like a molecule. Let's say this molecule here. So let's say we have a molecule that looks like this. And say, okay, let's say this is H, this is H. This is a H here. Say this is what basically is actually creating that. You see this here? Say this one's creating that doublet. What this tells me, this formula, is that n equals 1. It means the actual carbon next to it, as you can see, this carbon here, has to have 1 hydrogen. And it is true. That's what it basically tells us about the structure. So it does tell us about the structure. But not the most crazy stuff. But yeah, it does tell us something about the structure. So basically, yeah, it's just using the n+1 rule. So it's only 1 mark, so we'll just say using the n+1 rule. It tells us that on the adjacent carbon, there should be a 1 hydrogen. So using n+1 rule, the number of hydrogens is 1 in the adjacent carbon. Beautiful. Done. The 13 carbon NMR spectrum of molecules, so we have 1, 2, 3, 4. We have 4 carbon environment, basically. Let's write that down. Okay. In the space below, draw a structural formula of the molecule that is consistent with the information provided in part A to C. Alright, so how would I draw? Well, let's think about the possibilities first. We know it has this molecular structure or formula. So it could be a ketone, because a ketone normally has one oxygen. Or it could be an alcohol, like a OH. That could also be, it could be an aldehyde, also true. So yeah, it could be a lot of stuff. So let's start with alcohols. Let's just draw some structure of alcohol. So it's a C5H10. Let's go down here. C5H10 oxygen. Let's say we draw an alcohol. So CCOH. And so this is our alcohol. Now let's have a look if it's consistent. Now, because there's no symmetry, there's 1, 2, 3, 4, 5. We have 5 carbon environments, which is rubbish. We're supposed to only have 4. Not that one. So let's about if we create some symmetry. What about if I do this? If I, for example, take this part here and then put C here and C here. Now there is there is like overall now you know, what's happening to me? There is symmetry because of these two. They're symmetrical around that C. So we consider them as 1. So these as 1. So 1, 2, 3, 4. Now we have 4 carbon environments. Good. But does it fit our proton, which has the NMR? So 3 hydrogen environments. We have 1 here. Because of okay, these are considered. So okay, we would consider how many? Let's look at this. How many hydrogen environments? That's going to be 1. Oops. That's going to be 1. That's going to be 2. That's going to be 3. That's going to be 4. That's going to be all. These 2 are 5 because of symmetry. So there's 5. That's wrong straight away. So that's a problem. So we did that. We could. Okay, what about if I do this? So you kind of have to play around just to see which one works. What about if I put this oxygen? If I do this. Let's rub these out. OH here. Let's see what happens here now. But what am I doing? So sorry. Wait. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No, I am such an idiot. I'm not even hitting the hydrogen. It cannot be this. No. Wrong. Wrong. Absolutely wrong. What am I doing? So it has to have like a double bond somewhere. So let's say we had a double bond here. That takes that and that takes that out. So it still wouldn't work because you got what symmetry. That's considered, so that because of symmetry, that's considered as 1 carbon environment. These 2, that's 1. That's 2 carbon environment. Doesn't work. So damn, I don't think it's even a oxygen, like a alcohol group. So take that out. It doesn't even really work. Let's try a ketone. Damn. Yeah, I didn't even look at the 10 here. Okay, so a ketone, it has to have a double bond somewhere. So a ketone, let's say we start with like a midway ketone. So it's between, let's make it symmetrical right now. Let's see how that's going to work for us. Like that. Okay. How many carbon? So that's 1, that's 2, and that's 3. So we have 3 carbon. Nope, does not work. So we have to kind of, what about if I put this here? If I put it on the next carbon here. What's that going to do now? Let's have a try at this. So we have now, because there's no symmetry, 1, 2, 3, 4, 5 still doesn't work. Okay, we have to create symmetry. What I'm thinking is, what about if I do this? If I rub these 2 out and put a C here and I put a C here, does that work? Now there's symmetry. So because that's going to, 1, 2, 3. These are considered as 4. So, okay, 4. Does it hit our proton? Which is 3 hydrogen environments. So let's check how, oh my God, if it does. Let's double check, come on. So that's going to be, because of, symmetry, that's 1, 2. Oh, sorry, I forgot 1 here. 3. There it is. This would be considered as 3 hydrogen environments. Beautiful. So we've hit that. I just want to make sure it doesn't hit our molar mass. So 3. Yep. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, it does. This is perfect. This is our structure. Damn. Okay, that took so long. I'm not gonna lie. This was good. Okay, this is good. All right. So let's write that down. So C. Let's write it nicely. So you have hydrogen, hydrogen, hydrogen. Double O here. C and a H here. Hydrogen, hydrogen, hydrogen. hydrogen, hydrogen, hydrogen. All right, so that is perfect. So I'm gonna take this. There it is. That took quite a long time, but yeah, that looks nice. Like, it does fit everything that we've done. And does it even, you remember that we said that there has to be a hydrogen that has to be in one of the carbon? Yep, that's that one. Beautiful, so it fits everything. All right. The infrared spectrum of a molecule V is shown below. Explain why different frequencies of infrared radiation can be absorbed by the same molecule. Easy. Now, remember, the same molecule can have different... remember what infrared does. Infrared, it basically emits infrared light, and basically the molecule absorbs that infrared. So remember, different bonds, basically what am I saying? Absorb, different frequencies. There's basically the wave number. The wave number is your frequency. Like, for example, let me explain. If you use your go down to your infrared part. Where is it? There it is. Your infrared's here. Have a look at this. Your infrared, basically, different frequencies are produced because we have different bonds, different functional groups. Because remember, a molecule could have totally different, bonds. Could have a double bond. It could have, different functional groups. And basically, these are what basically create those frequencies. And also, other stuff that can actually also affect it is, for example, the size of the molecule. If the molecule is very large in size, it's going to basically absorb much more of that infrared. And so it will need more energy to vibrate and stretch to create those wavelengths. Also, something we could talk about is bond strength. Bond strength, some have stronger bonds due to electronegativity. Let's say you have a molecule that's more electronegative. It means that its bonds are very stronger than the normal parts. So that's why you could have totally different frequencies, and that's, yeah. So basically, a lot of molecules are different. Most of the molecules totally have unique infrared because they're totally different. You're considering everything: size, strength, bonding, electronegativity. These are all different for every molecule, and so that's why I think, yeah, absolutely. That's why it creates all these different frequencies for just only one molecule. So yeah, hope that kind of makes sense. It's the right one we just said. So 3 marks. Wow. All right, let's write down some stuff. Okay, so we said that the different frequencies. So the different frequencies are produced by the different functional groups and bonds. So functional groups, we said first, functional groups and bonds that the molecule has. These all have different. So these all have different bond strengths, basically bond strengths, sizes. We said electronegativities, and these are extracted. Of course, there's so much more that my brain can't even bring up. But yeah, fuss. We can say fuss. Each bond requires different amount. So different amount. Let me write it nicely. Amount of energy to vibrate and stretch, leading to different wavelengths. Beautiful. That's what we just said, different wavelengths. Because remember, your infrared, what it does is, yeah, you remember a molecule absorbs. It's not like it allows. It's not it's totally different from like allowing electrons to get out of it. It's basically it gets enough. It consumes enough energy, so basically its bonds stretch, turn, stretch out. They do a lot of stuff, vibrate, and that's what it does basically, and that's what it measures. So, yeah, I hope that makes sense. Hopefully, I should give the 3 marks. Maybe if I missed something, yeah. All right, question 8. Let's have a try this question. Let's use a different color. Let's use this red. A student performed an experiment to compare the energy content of a dry broad beans and dry soybeans. The student followed the method below. So when you're reading these questions are so common in exams now. So when you're reading them, look straight away for mistakes, things that they're making some little mistakes on. This is what you want to look at when you're looking at these questions. Read the method and see what he's done stupidly. Before even looking at the questions, look what he could have done better. So think of some mistakes, think of some safety hazards he's done, which is great. Think of the stuff, highlight them, that we see. Fill a 2-liter beaker with water and let it sit for 4 hours to come to room temperature. Beautiful. Crush 2 dry broad beans to a powder. Beautiful. So when you're crushing those beans to powder, why is that? Because we're increasing the surface area. And if we increase the surface area, it's going to basically have a higher rate of reaction. And then basically, that is the main function of crushing those powder. Weigh and record the mass of the dry broad bean using a clean watch glass. Okay, nice. Set up the equipment on a heat-proof mat as shown in the diagram. Yep, beautiful. A heat-proof mat. So it's a safety way, to make sure safety is concerned. Okay, so we have a 1 liter can here, watch glass, dry broad powder, heat-proof mat, and holes. Now, these holes, basically, why do we have these holes? Because these will allow combustion reactions to happen, not an incomplete. So we have to have those holes to make sure complete combustion occurs. So basically, remember, if it's a yellow flame, if you look at a Bunsen burner, if it's a yellow flame, that's incomplete. But when you look at a blue flame, that's a complete combustion. That's why we allow these holes here to make sure that complete combustion occurs. So ignite the dry broad beans powder. So they ignite it. Okay, so they ignite it and suspend the 450 water can containing 300 milliliters of water directly over the burning dry broad beans powder. Wouldn't you normally flip these around? For example, okay, they basically, let's say you have let's say you have a can here, and say you start burning the fuel. You're burning it, and some of the heat would have already been gone until you would have put the container in there. That's what they've done. So they first ignited the dry broad beans. They ignited it before even putting. So the best way they should have done is they first should have put that actual container in there, and then they should have turned the dry beans. They should have ignited that dry beans. So all of the energy would have been consumed out of dry beans. Now this basically this is like a little error that they've probably done. Here we're just basically looking at it through very detailed. So I think one of the best ways they should take care of it is basically to make sure it's normally put that glass first. So basically, step 6 should have been first and 5 would be better. But so now this could have basically introduced some error. That's what it would have done. So we have a digital formula. Beautiful. So metal skewer, 450 aluminum, which 300 milliliters of water, 1 can, watch glass and ignited, dry broad beans, heat-proof mat, holes. All right, so record the temperature of the water in the 450 milliliters can every 30 seconds until the dried broad beans have stopped burning and the temperature of the water has begun to drop. When the temperature of the water is 450 in the 450 can is below 300, empty the water for the 450 milliliter can and wait until both cans return to a room temperature. Beautiful. So he's waiting for them to return to normal temperature. Repeat steps 2 to 8 using dry soybeans instead of dry broad beans. All right, that's not too bad. A. Explain why the dry beans were crushed in step 2 on the experimental. Beautiful, like what we said. So basically this will increase surface area, hence increase rate of reaction. That's it. So increase surface area was 1 mark and increase increase rate of reaction. So different color. Okay. Identify the dependent variable in the experiment. Remember, your dependent variable is what you're measuring. What you are measuring. What is the main focus? So when we were looking at here, it was the energy content. That's what we want to. We want to compare the energy content between dry broad beans and dry soybeans. So basically, the type of beans is your independent variable. So the dry broad beans and the dry soybean, the type of that dry bean is your independent variable. Your dependent variable is what you're measuring, which is the energy content. So energy content. identify one step in the experimental procedure that is designed to manage safety hazards. Explain how this step reduces the risk associated with the experiment. Beautiful. I think the most easiest, like we said, was the heat-proof mat. I think, you know, using that, like, one of the most easiest is using the heat-proof mat. Basically does not ensure like the lab bench gets heated, and hence like it decreases the risk of fire. Like, it's so easy. Just, yeah, there's other parts, of course, like there's other parts, but I think that's the easiest one to put. So let's put that one there. Do we need to, what is it? Identify this one step. What step was that? So, 4. Yep, so 4. The one that, so step 4. Say step 4. Basically using a heat proof mat. So basically this ensures that the heat does not spread through the lab bench, basically the lab bench. So for the lab bench, hence reducing the risk of fire. Reducing the risk of fire. So step 4, using a heat-proof mat, this ensures that the heat does not spread through the lab bench, hence reducing the risk of fire. Beautiful. We have explained the, yep, beautiful. D. When the experiment was undertaken with 1.1 grams of dry broad beans, the following results were obtained. Okay, mass of the broad beans with this, and the initial temperature of the water and the final temperature of the water. Use the experimental results to calculate the energy content of the dry broad beans in kilojoules per gram. So we want kilojoules per gram. So we want the first energy. So the energy is quite easy because it's the amount of energy that the water has absorbed. And so you remember E mc delta T, that's the equation. So what was the mass of the water? It was 300 milliliters. So to make sure it's in milliliters, we have to make it to mass. Now, 300 milliliters, to make it back to make it into grams, we basically have to multiply it by this constant. Where is it? 0, this one here. So 0.997, which will give me, bring it back. Yep, so this will give me 300 times 0.997. Basically will give me 2991 grams. And so now, let's write that down. 2991 grams times your specific heat capacity of water, which is 4.18, times your delta T, your change in temperature, which they have given. So that's your final minus your initial. 32.1 minus 25. That gives me 1 minus 25. That gives me 880.76.69 joules. Make sure you divide it by 1,000 because we want it in kilojoules. So divided by 1,000, you should get 8.876 kilojoules. And so basically get that. And to get the, in terms of kilojoules per gram, so kilojoules per gram, which is your combustion, it's your kilojoules, so that 8.876 divided by the grams per gram, which we use how much? We use that much, 1.11. And that gives me 1.11. So how many significant figures we want? 3. So we basically, it's actually just 8.00 kilojoules per gram. Done. That was not bad for 4 marks. That was very easy. The typical nutrition content of a dry soybeans is provided in the table below. So wait, what did we just calculate? Was it? Yep, for dry broad bean, this one's for dry soybeans. Okay, we have the protein for the average quantity of 100 grams. We have how much protein? 36, fats 20, carbohydrates 29. Using the information below from the table to calculate using the information nutrition from the table to calculate the heat combustion of a typical dry soybean in kilojoules per gram. So remember, we want it in kilojoules per gram. So we want the first energy in kilojoules. So easy. If you go to your table, go down to the There it is. So energy content for food groups. So we can see that, okay, we have first protein, which is 36 grams we have. We multiply that by how much is protein, kilojoules? 17. So it give us 17 kilojoules per gram plus 20 grams of fat, which is times 37 plus 29 times, that's our carbohydrates. So carbohydrates gives us 16. That is it. So let's go back. So that should give me my energy in kilojoules. 36 times 17 plus 20 times 37 plus 29 times 16. So that's giving me 1816 kilojoules. So I got that. Now remember, to get the enthalpy change, your combustion reaction, it's that kilojoules, so 1816 divided by the grams of how much we use. We used per quantity of 100 grams, so divided by 100. That gives me how many is it going to be? 2, so 18 kilojoules per gram. Nice question. When the experiment was performed using with a dry bin, the heat combustion was found to be 35.5 kilojoules. What? What the hell? 35 point. This was supposed to be around 18 kilojoules. How the hell did it go above and beyond? Normally they tend to be lower because of heat loss. How could it be higher? So there's a big error here. So suggest one experimental error that could have caused the experimental value to be different to the heat combustion of a typical dry soybean. Explain how this error could have caused the difference between the experimental results and the expected result. Ooh, a little bit hard. Could it be because I was going to be like, no, what can we say? There's so many ways. Wait, could it be because, let's say it was heated, and so the aluminium basically was retaining some of that heat, and so when it finished combusting, still that aluminium was still heating that water? But that doesn't make still sense. That would have underestimated because, still would have underestimated. It should have been, why is it overestimated? Still underestimated because if the aluminium retained water, because energy is constant, if the aluminium retained that water, it would have it would have given that same energy, and then hence we would still be close to that value. Why would it go above and beyond? Okay. What about the thermometer? What about if they place this thermometer actually like next to the bottom of the can, actual bottom next to that heating element, and so basically remember what they have to do is basically they have to stir it. They have to use that metal skewer. They have to use a metal skewer to basically stir it. Sorry, this thermometer in this can here. If they put it at the bottom of this can here, right in the middle or where the center of the heat's hitting, and say they didn't stir it up, if it's not stirred up, there's going to be at the bottom of the can, it's going to be of course hotter compared to the top. So if let's say they didn't stir it, or if you put a a thermometer right under and it touches the ground, touches the bottom of the can, of course it's going to be observing a higher temperature change. It's going to be a higher temperature change. And if you have a higher temperature change, remember, it will affect our energy because remember MC delta T? If your temperature change here is higher, it means then your energy is higher, and hence that's why it could have been overestimated. Yeah, I think that's a very reasonable. We'll say that. Yeah. So basically you could have had the thermometer right touching at the bottom, and it wasn't basically stirred. So at the bottom of the can, which is a big problem. So that will, overestimate it. Let's write that down. For 2 marks. Okay, so I'm going to kind of go in detail. I want to go in detail with this one, just to explain it, so when you read it, so you can really understand what I mean. I'm going to try to be in detailed. Yeah, I know it's 2 marks, but because I want you guys to understand what I'm writing, and so if you don't understand, this is what I'm talking about. So basically we could say an overestimation. So overestimation of the change in H could have been caused by the thermometer, if it was let's say, so if it was at the bottom of the can, it could have been in direct contact with the can. So in direct contact. So it could have been in direct contact with the hot can, or what? It could have been direct in contact of the hot bottom of the can. So okay, it could have been direct contact with the hot milk. Then another station of the change could have been caused by the thermometer. If it was at the bottom of the can, it could have been in direct contact. It could have been in direct. What am I repeating myself? It could have been in direct contact of the hot bottom of the can, and not measuring the in direct contact of the hot bottom, and not measuring the temperature of the water. The temperature of water, but the bottom of the can. I'm not writing that because it's kind of like repeating itself. And we know it's going to be, of course, at the bottom can much higher. So hence, as a result, the thermometer would record a higher temperature change, a higher change in temp than the actual actual water temperature. Beautiful. And how would this affect? So explain how this error could have caused a difference in the expect. Okay, this, what would it be? Well, it would increase change in temp using Q is equal to MC delta T. If T increases, energy basically increases. Hence, the higher energy content. Hence, the higher energy content. I mean, I'm just mumbling at this point. There it is. I think that's enough. Yeah. So as an overestimation of the 2K, okay, it could have been dark contact of the hot bottom and not measuring the temperature. Beautiful. As a result, the thermometer would have recorded higher than actual temperature. It would increase the change of hand. So if change in T is increased, energy increases, hence the higher energy content. Beautiful. That works. F. So suggest one improvement to the experimental method using the apparatus and the methods shown on the page so that would produce more accurate results. Explain how this improvement could improve the accuracy of the results. I'll be honest with you, you remember how we talked about how they could have basically switched B and 6? 5 and 6, steps 5 and 6. That was it. Because they should have put the water the can directly on top of the heating element before even heating the soybeans, because energy would have been lost. And this basically would have created error. Significantly systematic, because if you kind of think about it, if you have say they already heat was lost a little bit, but then they put the container on it, so then of course the water will be heated at a constant rate, blah blah blah. But if they put it, let's say they started the experiment, but they put the heating can before lighting it up, what would happen is the energy would basically increase the temperature quicker, systematically still. But yeah, you can see that there was an energy loss. If this was I think if this is temperature and this is time, yeah, this is how it kind of would look like. Basically, it is systematic error. It would mostly affect systematic error because, yeah, I hope that makes sense. A little bit hard to kind of explain. All right. So write that down. So basically switch those up. So for 2 marks, beautiful. So what they could have done is, instead of first igniting the sample, and then suspending, suspending the water can. An improvement, so we want to improve an improvement that can be made, is first suspend the, was it 450? 450, yeah, milliliters. Okay. Suspend the 450 milliliter can of water, of course, of water, before igniting the powder. This decreases systematic error, hence increasing accuracy. Beautiful. Write a valid conclusion for the experiment based on the experiment result. Very easy. Writing conclusion is so easy. To write a conclusion, you just need to say what is the obvious. So you need to include the dependent and your independent variable. For example, now what do we know? Like, what was the overall result? We learned that what? So wait. We learned that. Okay, where was this? We learned that. Okay, the dry soybeans gave us that energy. Doing calculation, gave us 8 kilojoules per gram. And for the dry soybeans, it gave us 35 kilojoules. Overall, you just say this. In conclusion, the energy content of the dry soybeans is higher than the dry broad beans. That's it. You see how we basically answered our aim? So we included our dependent variable, energy content. That's our main focus. And our independent variables, we know that the dry soybean is higher than the dry broad beans. It is so simple to write a conclusion. You just need to write the most simplest. It's only 1 mark, so very, very easy. So we can say in conclusion, the energy content of dry beans, dry soybeans. What am I saying? It was dry soybeans that was higher. Dry soybeans is higher than dry broad beans. So that is it. That's all you basically need to do. Next question, question 9. Purified copper contains at least 99.8% copper. Purified copper is used in electronic devices because it is a good electrical conductor and resists corrosion. Purified copper is produced from the impure copper by electrolysis, okay? The electrolysis cell is shown in the diagram below. The impure copper contains 99% copper. The remainder of the impure copper consists of zinc, lead, and gold. Alright, what else? So we have the impure, okay. Use your understanding of your electrochemistry to discuss how electrolysis is used to purify copper using the cell above. In your response, provide a definition of electrolysis. Explain what happens to the gold, zinc, and lead in reference to the electrochemical series. Now, the most easiest mark is just to define electrolysis. Remember, what is electrolysis? It's just a non-spontaneous redox reaction that requires a power source to occur. That's it. It is so simple. Electrolysis, non-spontaneous, requires a power source to occur. Whereas galvanic cells, spontaneous, does not require power source, and it's that is easy. So electrolysis defining, that should give you 1 mark. The other mark is basically coming from explaining what happens to the zinc, gold, and lead. All right, and how do we do that? Well, let's use our electrochemical series. Let's predict what's going to happen. That's the key, because what we overall want is we want to purify that copper. We want to take that copper and basically electrolyze it to make it more purified. So let's do that. Okay, I'm going to use the electrochemical series. Go up here. Let's rub these out. Okay, let's see what we have. What's it? Sorry, let me just... There it is. It's work. Okay. I don't know what just happened to my Apple Pen. Okay, let's do it. So what do we have? Well, what are the components? Well, we know it's aqueous, so there is water. So we can say we have this water here that could react. We could have this water. We have, of course, copper 2+ ions. Copper 2+ ions. We have, in that impure copper, remember we have copper, normal solid copper. We have zinc. Where is zinc? So zinc, of course, in solid form. What else? Zinc, Pb, which is your lead, and your Au, which is your gold. Anything else? We do have H+ ions here, but I don't think they're going to be any. Let's write that H+ ions here. Done. So these are overall what the components that we've seen. All right. Now, to get the marks, you just basically explain what's happening. So let's have a look here. What is our strongest reducing one? It means what's our strongest oxidizing agent? Remember, it's on the left, and it's the highest one on the top, the left, on the left-hand side, top, which is just copper. So basically, copper reduces to create copper solid in the cathode. Remember where the cathode is? The cathode is going to be here. And this is our anode. Easy? So basically what's going to happen, of course, electron flow goes through this one, positive, negative. Beautiful. So basically in the cathode, we're going to actually get copper solid, which is great. That's actually very, very good. And so in the anode, where basically oxidation occurs, which one's the strongest oxidizing? So which one's the overall strongest reducing agent, in other words? The one that goes down and it's on the right-hand side. Well, first it's zinc. So what's going to happen? So zinc in the impure copper is going to basically form ions. It's going to form, so it's going to form zinc 2+ ions, is it? Yep, 2+ ions, because it's going to transform there. And then, after the zinc finishes, so after zinc basically finishes, because there isn't a lot, of course, and then the strongest, how did I write Pb here? Okay, and the next one is your lead. That's the strongest. So it's going to also form Pb 2+ ions. So, okay, we formed those ions. What else do we form? How did the Au get out? Okay, so we formed all those. Now, guess what we're only left out with here? We're only left out with Au and copper. You know that copper, 99% copper. All right. The next one that's strongest is the copper itself. You can see that copper itself is the strongest. Hence, it's going to create, now it's like the strongest oxidized one, or the strongest reducing agent in the system, and hence it's going to form more copper 2+ ions, which is great, and hence it's going to form again copper solid, which is good. So that is actually good, because now we are going to be able to form that pure copper is going to go on the cathode, which is our goal. That's what we want. We want to make sure we only take that pure copper. But then that Au, that is not what we want now. We don't want gold. We've hit our gold mark. We've hit the gold mark. We've taken all that copper. Now there's a gold left out here. There's left out here. We don't want anything to do with it to go to our cathode, because remember, now we've got pure copper. That's all we need. So, we don't want to even, we don't want basically this to react. That's our goal. We don't even want to touch it. But then you're like, what happens to these Pb 2+ and zinc 2+? Well, they're quite useless, to be honest. Let me explain why. If you form them, so imagine you form this one here and you form this one here. Well, what's still the strongest reducing agent, oxidizing agent, so the one that basically gets reduced, is still copper. Copper is still top. And it's still forming that copper solid, which is our goal. So they're quite useless, but it's good. You know why? Because we took them out of this impure copper. That's our goal. And this is what the big problem is. If we actually allow, gold to basically, in other words, oxidize, it's going to form Au+ ions. Now, okay, we form Au+ ions. What would that do? That's a big problem, because now it is the strongest reduced one. It's stronger than that Cu2+. Hence, it's going to form gold plating around the pure copper, and that's not what we wanted. That's not our goal. So that's why we be careful. We don't want to touch the Au. So we want to basically have, and how do we kind of we want to basically let that gold stay in that anode. Basically, we just want to leave it there, leave it by itself. We don't want to even touch it. And so how do we prevent it? Well, the best way is actually to make sure our voltage is restricted. Make sure the voltage is restricted. We can have any voltages around from here to basically here. Not here, but like the AU basically here. These are the voltage range that we can have that will make sure that this AU is not going to be able to react. Why? Because if you give a voltage that's greater, let's say this voltage here. Now, can you see how AU is now higher? So if you create a voltage, it's able to basically react, and that's not what we want. So make sure we want to have a voltage around this part here. This part over here, only from there to there, because remember, it's enough voltage that it will react the other stuff that we want, which is great. You know, that zinc, that lead, that will take them out of that impure copper, and yeah, and so that is our main goal basically. That's what we want to do basically. I hope that kind of makes sense. I think I'm gonna write a lot, try to explain it in my writing. I know I'll talk basically a lot, but that's my goal right now. Let's smash it. All right, let's go. Okay, so first of all, what we said was, just talking about the definition of electrolysis, what we said was it was a non-spontaneous redox reaction that requires, requires a power source to occur. Power source to occur. That should be that first mark, that easy first mark. Next one, it's just basically writing the equations that we've learned. So we know what we said was, what was it? What was the strongest first? It was the strongest oxidizing agent was the first Cu2 plus. So Cu2 plus is the strongest oxidizing agent. So it's the strongest oxidation agent, and hence will reduce, and hence will reduce to, so it will be, the formula is Cu, let me write it in a different color a little bit, Cu2 plus aqueous plus 2 electrons gives us copper solid. And so it's going to act at the cathode, basically. In the cathode, which is the negative terminal in electrolysis. Cathode in the negative. So I think I'm writing too much. So it's in the negative terminal. Done. That's good. Now the strongest reducing agent, which was the zinc at first. So let's write that. So the strongest reducing agent. So agent is zinc solid, which basically oxidizes, to, so it's going to be zinc solid, zinc 2 plus, AQS plus 2 electrons, which occurs at the anode, basically, which occurs at the anode, at the positive terminal. So like positive, let me write positive. So basically after zinc is electrolyte, so basically it's gone. Electrolyzed. No, that's, yeah, electrolyte, probably spelled it wrong. Then it's the lead, so your PB is the next strongest, reducing agent, basically. Reducing agent, and will oxidize. So oxidize to PB solid. So it's PB solid, and it goes to, we can see that it's PB 2 plus AQS plus 2 electrons in the anode. Done. There's a little bit in detail for the first marks, of course, but it's kind of, hopefully when you read it, it's kind of understanding. Now I'm going to write more to kind of go into the depth of what we were supposed to do. So what's going to happen? So basically, after zinc and lead basically oxidize, like we said, they'll be left out in the electrode. So that's what we're going to say. After zinc and Pb have oxidized, they will be left out. So they will be left as ions in. So they'll be left as ions in the electrolyte. Hence will reduce. Wait, so electron and hence. What am I talking about? Hence with the ions with the. So electrolyte, not hence. Alright, so have oxidized. They will be left out as ions in the electrolyte, and basically after they've left ions, we only have Au, so gold and copper left out in the anode basically. So that's what we're gonna say. They've electrolyzed, and hence the only thing left in the anode is Au and copper. Beautiful. So copper will become what? Yep, it will become the strongest new reducing agent, basically. Copper is the next. So it's the next strongest reducing agent. Strongest reducing agent, and hence will form Cu2 plus ions. So, and hence will form Cu2 plus ions. So, and hence will form Cu plus in the electrolyte. So electrolyte. And hence this will reduce to form pure copper. So when it gets this, it will reduce more to pure copper. Hence will reduce to form pure copper. Will reduce to form pure copper. Wow, that's a lot of writing. We still have, because I still have more. And basically what our goal is to make sure is that gold should not be oxidized, because remember what happens if it gets oxidized, then we form Au2 plus ions, like we said. We form those Au2 plus ions, and then the next, basically the strongest oxidant that will happen is that Au plus, and hence it will basically reduce to form Au plus ions. So there will be a layer of gold in that pure copper, and that's not what we want. So copper, what else do we say? So we say Au should not be oxidized. So Au should not be oxidized, as if it is, it will create Au plus ions, and hence, oh my god, I'm writing a lot. And hence, those ions are a stronger oxidizing agent. Than Cu2 plus. Yep, that works. So then Cu, which means this means that Au will form a layer. In the pure copper. So we'll formula which will decrease purity, basically. Which will decrease purity. That's a lot of writing, I'm not gonna lie. So which will decrease the purity, that's main. And so to make sure that does not happen, that's our goal. So remember what we said, to make sure that does not happen, we need the voltage to be between 136 volts to 0.3 volts. And this will make sure that basically AU would not oxidize while the other ones becomes, the other ones oxidize. So I think that is also important to write. So that's what I'm basically going to have to write. I'm going to just make some space. And I'm going to make this, I'm going to just move this whole thing. It is a lot of writing, but I hope that kind of makes sense. If it's in detail, that's what my goal is. If it's, oh my god, why would it not move? There it is. So there it is. So let me just move it here right now. And let me just write the extra last parts that I want to talk about. So we said, let's use, what color, let's say. Let's use blue. So we want to talk about how to make sure that does not happen, we said. So, to make sure that, this does not happen, we can basically like restrict it. So we need a voltage. We need a voltage between, let's think. So it was between what? So between 1.68, not equal to it, voltage, less or equal to 0.34. It's a little bit maths. These are inequalities, of course. But, of course, we don't want it to be equal to that 1.68 because if it is equal, what happens? It basically will become it will react. And we can actually let it be 0.38 because that's where our copper is. And, yeah, that is our basically like the domain of voltage that we can actually have. And this, as this will make sure, AU solid will not oxidize. Will not oxidize while the other processes, we'll say other processes occur. Yeah, I mean, yep. Does that a little bit extra? So, and probably a student, like we said, you know those zinc? You know that lead and zinc, why do they not affect that? Because remember, they are lower than, so, you know when we form them, like we said, when we form them, what happens? They are useless because still copper is stronger. It's the strongest reduced one or the strongest oxidizing agent. So they don't actually have an effect. So, but it was good that they kind of left, and so they'll stay in the electrolyte. So they won't have, so we'll probably say that last part. So the zinc ions and so zinc 2 plus and Pb2 plus have no effect, no effect on electrolysis, as Cu2 plus is a stronger oxidizing agent. Basically, they won't react and stay in electrolyte. I'm not going to write that, but that's a lot of written. So hopefully that kind of is in detail, very much detailed. Even though it is a lot, but I hope that when students kind of read this, they can understand the detail that you kind of want to, Of course, not this detail, but it does hopefully hopefully it will help students understand the question, how to answer it. But I don't know if it's the perfect answer. That's the problem. So I need to double check this. But yeah, there it is. Last question. Oh my god, 3 marks. Okay, let's just smash through this question. For Faraday's first law of electrolysis, it states during electrolysis, the amount of chemical reaction which occurs at any electrode under the influence of electrical energy is proportional to the quantity of electricity passed through the electrolyte. Easy. Remember, Faraday's first law states, basically let me explain this in much more basic terms. It states that the charge is proportional to the amount of mass that is going to be formed or electrolyzed. So, for example, if you put more electricity or more charge or more like current you're basically going to increase the mass that's going to be formed when you're electrolyzing. That's what it is. That's what Faraday's first law basically is in the most basic, simple terms. And so, yeah, that's what it is. And so it says, explain how Faraday's constant F, together with Faraday's laws of electrolysis, can be used to find the amount of bromine produced when molten potassium bromide is electrolyzed. This is such a beautiful, easy question. 3 marks, and it ends the exam nicely. Because that question that we just did right now ate my head in. This is a beauty right here. So, what do we do? Well, first, I think the most important thing, it's so easy because all we need to do is this. Using our, of course, your Q equals, remember? Q equals, what am I doing? Current times T. We just need to find the current and the time to give us the charge. And this charge, we can use Faraday's constant to get the number of moles of electrons. Because remember, it's Q over F. Remember, Faraday's constant is a constant. We're basically going to be describing everything that I'm right now going to say here in words, basically. So using this, we get the number of moles of electrons. And basically, using the equation that we know of bromine, which you'd find, of course, in the electrochemical series, we can easily find the number of moles of bromine that will be formed. And that's it. That's what basically this whole equation is. And now we have to just kind of write it all in words. So it's such a nice, easy question to kind of end it. All right. So first thing is, let's find the equation. So let's just first say when, and these are molten, so there's no water, which is so easy. When molten, okay, Br liquid is electrolyzed. So what's going to happen? Let's check. So let's just rub this out. Let's kind of know what's going to happen. Okay, wow. Let's just cut this out. Okay, so Br minus, where are you? Here it is. Br minus is here, and K plus ions would be here. So the strongest, basically reduced one, or the strongest oxidizer, is this Ka aqueous, and hence remember, if it's basically being reduced, it's going to occur at the cathode, and so we can write that down. Cathode dot is basically K plus aqueous plus electrons go to K solid, and so in the anode, it's going to be 2 bromine. So, 2 bromine aqueous goes to bromine to liquid plus 2 electrons. Done. So we've written the equations, and so now we just basically state Faraday's law, and let's do some calculations and explain how we're going to calculate. So, according to Faraday's first law, which states that the charge, so charge, which is Q, your charge that is given will be proportional to the mass of, we want bromine, so Br2 produced. And now we'll just explain how to do it. So using Q equals IT, so the current time, we can calculate the amount of charge, and hence when we calculate that charge, and hence using this, number of moles of electrons is equal to Q over F. Remember, F is your Faraday's constant. We can calculate the number of moles of electrons. Basically using Faraday's constant. So let me write that down. Using Faraday's constant. Done. Which is basically like, 96500. Okay, so using the oxidation reaction, so where is it? Where's the oxidation? Yes, it is. So because electrodes on the right of bromine, using the oxidation reaction. So using oxidation, basically, let's see what's happening. So basically, when so we got that 2 bromine here. So basically, using this oxidation reaction, what do we get? So we get 2 bromine. Aqueous gives us. So this is what we want here. 2 bromine, and we need 2 electrons. So basically, so using our oxidation reaction, we know that when 2 moles. So we know that when 2 moles of electrons are produced. Also, yeah, 2 moles of electrons are produced. 1 mole of Br2 is produced. Hence, the mole of Br2 can be just calculated by. So I know it's 1/2 of the number of moles of electrons, basically. And yeah, that's it. Because the number of electrons will give you the amount of bromine. The amount, not in mass. They're not saying mass, but amount means mole. But basically, yeah, that is it. I think that goes in very much detail for those 3 marks. And yeah, very nice, easy questions to end it with. Very, very easy. A little bit, this was kind of difficult because I think it's a lot of wording I think I wrote, but hopefully it goes in detail. I hope you guys enjoyed this video, and I hope it helped you in any way. Please make sure to like and subscribe for more future videos like this, and I hope you guys have a great day. Bye-bye.